Thanks. Okay, I don't want to cut into his 50 minutes, so without further ado, we have Mohammed Omar speaking about using slice rank and partition rank.
All right, so thanks for the invitation to speak here. So I have a couple of announcements before I start. So one of them, both of them are for people who know me. So one is, you might see this sort of affiliation change. So after a decade at Harvey Mudd, I'll be moving to York University in the lovely city of Toronto, Canada, which is my hometown. So lovely there. Another quick announcement is, so I actually did my PhD here, so it's actually really nice to be back in Davis after a long time. For graduate students who are here, there's an awkward photo of a kid out on top of a board in the big office. That's me, so if you ever were mysteriously wondering what that's about, now that mystery's over. Okay, so let's get into the math here. So today I'm going to talk about something that I've been playing with for the past sort of year or two, about 2 years. And I think the moral of this story really is so I work in enumerative and geometric combinatorics, and I think especially early on in our careers, we tend to work on sort of the staple things that we're very comfortable with. And sometimes it's nice to just get out and look at the broader world of mathematics and see where some of the things that you're familiar with can actually have some influence. So instead of sort of telling you about things that I discovered, what I'm going to do is take you through the process of what it felt like learning this stuff that's outside of my area, and then seeing how the tools that some of the tools that we're familiar with can help in discovering in that land. Okay, so I think my clicker is not working. Okay, thanks for your time. Oh, there. Button. The what?
The bottom one.
Oh, okay. Okay, so so I'm going to talk about these ideas of different tensor ranks. I'm not going to talk about them in terms of tensors. I want to make this just like very basic, bare bones, and accessible. So the basic idea behind these ranks in applying them in combinatorial situations is if you have a finite subset of some vector space that avoids a particular property, your goal might be to maximize the size of this set. So this is stuff that extremal combinatorialists think about all the time. And I'm going to talk about how through reading a bunch of the work that these people did, I sort of noticed that lurking in the background, you could infuse things about partition lattices to take the material and unify it, and then also find interesting applications. Okay, so for the first half of the talk, I'm going to sort of tell you about what this, mainly slice rank, what it is, how it was used to make large breakthroughs in extremal combinatorics, and go on from there and how I sort of jumped in. Okay, so I'm going to think about this sort of simple seeming extremal problem. So you have a subset of an n-dimensional vector space over F3, and we'll call it a cap if it has no 3 collinear points. And so the question is, how do you find this number parameterized by the dimension of the space, which is the largest subset of this vector space that avoids having this thing? Okay, so you know, if you're like playing around with this stuff, if you're sort of doing it from scratch, you start with small values of n to explore. So here's n equals 2. It turns out that the largest size of a cap set is 4. Here's an example of one. If you wrote down the points in the space, pick these 4 points right here. And you might notice that there's this diagram on the left that looks like a bunch of cards from a game you might be familiar with. So this comes from the game set, where you have a bunch of cards that have shapes, numbers, filling and coloring of objects, and lines in here sort of correspond to sets in the game set. So something fun, but not something I'm going to really focus on. Okay, so in the land of the type of math we care about, you might think, is there a nice description of what this number is, maybe a generating function, et cetera, et cetera, et cetera. And you start to play around and you see that this number is kind of erratic. So even if you look at like old literature that establishes these numbers, even finding C of 4 uses like some Fourier analysis, right? So it's not, doesn't use a lot of tools that are used often in this community, and you can see that these sets are quite complicated. So instead of asking for the exact number, you might want to get a sense of how large these things are in general, right? What are the asymptotics of this particular number in terms of this parameter n? But first you might want to ask this question of why you would care about this. I mean, this seems like a very random, fictitious problem. Well, if you sit down for a bit, you'll realize that the condition of having 3 collinear points in this space is exactly the same as the condition of the 3 points forming an arithmetic progression, right? And so from the point of view of the people who work on this stuff, this is something that they care about quite a bit, is this question of having subsets of a given vector space that avoid arithmetic progressions. So this is central in additive combinatorics and number theory. And so a lot of people care about these things, and it turns out this problem of even understanding the asymptotics of this thing was daunting for a long time. I put in another stipulation or another condition here that's equivalent to having 3 collinear points, which is that in every coordinate they're all the same or all different in the field. And this will come up when I talk about applications later. And for those of you who like the set game interpretation of this looks very much like an encoding of the game set, where you have in every single characteristic, you have all cards being the same in that characteristic or being different. Okay, so let's look a little bit about or at the history of this thing. Okay, so here's an upper bound on the largest size of a subset of this vector space that contains no 3 points that are collinear, 3 to the n. Yeah, I mean, yeah, okay. Okay, so you can get an exponential lower bound as well. If you take all points with 0, 1 coordinates, there's 2 to the n of those. This number has to be at least as large as that, because if you have a collection of cards that form that avoid 3 collinear points, you can't have this situation here. So you can avoid having this situation where in some coordinate all 3 are different by just selecting all the points to have 0, 1 coordinates, right? So somewhere, this number is lying somewhere between 2 to the n and 3 to the n. So early on, there was an upper bound that took this 3 to the n and dampened it by a linear factor. This was a manageable thing to do. And it wasn't until 16 years later in a pretty strong journal that this was improved to something where you just like ever so slightly increase this linear factor, right? So this gives you a sense of the difficulty of actually breaking through this 3 to the n barrier using all the techniques that were built up to that point. Kind of surprising. And so, many people who think about these things ask sort of this question, is there an actual exponential upper bound that's weaker than the trivial one, right? So can we prove that this number is at most k to the n, where k is strictly less than 3, right? And there's this quote by Terry Tao is one of the most interesting, intriguing open problems in additive combinatorics and Ramsey theory for over 20 years. So at this point, I mean, you're probably really asking the question sort of like, how does this fit in formal power series and algebraic combinatorics? We'll see a little bit later how those techniques come up, or at least techniques that a lot of people in this community play with come up in applications of this stuff. Okay, so what I want to do is actually give you a sense of how this was finally resolved. So this was resolved in 2017 in a paper that was published in the Annals. And typically, if you read expository articles on this, it's accredited to two groups. So this group actually proved this sub 3 to the n upper bound for sets that avoid a triple of collinear points. And this group here did something very, very similar, but just in a slightly different setting. And the thing that's surprising about this, actually, is the methods that were used in the explanation of this upper bound is not really complicated, right? We'll be able to get through this in the next, 10 minutes or so. And then I want to tell you about sort of my explorations with this as I started reading similar types of articles that do similar things. Okay, so the proof sort of relies on something that was discussed in a blog article of Terry Tao after the papers came out. So he sort of had a nicer way of symmetrizing things and talking about them cleanly. And he introduced this concept called the slice rank polynomial method that I'll talk about now. Okay, so we're switching gears and thinking about something that has to do with some type of concept of rank on technically tensors, but I'm going to just talk about functions on k-fold products of sets. So if I have a function from a set, a k-fold product of a set x to some arbitrary field, I'll call it a slice if you can slice something off, right? So usually words are there for a reason. So in this particular situation, what we mean is you have this function of k variables. It's a slice if you can write it as a product of a function in one variable times a function in all of the other variables. So let's look at some examples. So this is a very benign example. You have a function from R3 to R. It looks like this. And, I don't know, algebra 1 or something, you factor out the x2, you notice it's a slice, right? But sometimes you have to think about this for a second to see that things are actually slices. So here's an example. You have a function from a finite field, three-dimensional vector space over a finite field of order 2 to that field itself. And the three variables where you have a polynomial like this. So there's actually two ways to recognize that this thing is a slice. Like you think to yourself, okay, you could factor out an x2, but then the function you're left with still has an x2 in it. So that's bad, right? But there are two other ways to recognize it. So first of all, in the actual field we're working with, x2 cubed is the same as x2, right? So just re-represent this and then factor the x2 out. There's an even more silly way to see this, which is there's no x3 here, right? So this function is a function in the two variables times an identity function, which is a function in x3. The reason I mention this is because this type of weird, funny thing actually comes up when you try to employ using this slice rank idea. Okay, and then if you take like an elementary symmetric function, we know you can't, over a characteristic zero field, you know you're not going to be able to slice it up, right? So it's going to have slice rank at least 2. Sorry, it's not going to be a slice. So what is the slice rank? So the slice rank of, I don't know why I capitalized that, is of such a function is the minimum number of slices you can write it as a sum of. Right, so in our example, our last example here, we know we can't write this as a slice, so the slice rank of this thing is at least 2. And it turns out, you can see pretty quickly, the slice rank is going to be exactly 2. because you can factor out x1 from the first two terms and then factor out whatever variable you want from the last one. Okay, so how does this play a role in the entire setting that we're interested in? This seems sort of completely removed from the idea of finding an upper bound on sizes of sets that avoid a certain property. So here's where a connection is made, and Tao wrote about this. So if you have one of these functions, and it is diagonal with non-zero diagonals, so what I mean by that is that this function is non-zero precisely when all the variables are equal, then it turns out that this concept of rank, the sliced rank, is actually the size of the underlying set itself. So at first glance, these two sort of don't feel like they're doing anything for the objectives we have. So, and this thing kind of looks a little bit mysterious if you haven't seen it before. So let me give you a sense of what the game we're going to soon play looks like. Okay, so it looks like this. So you have a set X that avoids a certain property. In our situation that we saw earlier, you avoid triples of points that are collinear. So what you'll do is create a strategically chosen diagonal function where here k will be 3. So you'll craft it in a way that it somehow encodes avoiding, or can be made diagonal while avoiding these triples of points. And then from this, you'll be able to say that the size of this set, which you find mysterious, is equal to the sliced rank of this function you created. And then the goal is to find an upper bound on the sliced rank using algebraic means, right? And that's exactly the process that we're going to see play out in a moment. So I should mention a little bit about why this is even true, though. So you can kind of see that an upper bound pretty quickly, regardless of the function that you pick. So imagine for a second that your underlying set was just the set 0, 1, 2, and you had a function from the twofold product of it to some field, right? Then you can always write this function in this way. Here, this is the indicator for x1 being 0, right? So if x1 is 0, then this will live, and you plug in f of 0 on whatever x2 is, right? Everything else here will go away. So, and you notice this is written as a sum of 3 slices because each of these individual functions on the right are functions of just the one variable x2. Okay, so the sliced rank of this thing will be at most 3. And then so the real work in this theorem is proving equality. And that's a kind of not too long linear algebraic argument. But what's more interesting for our purposes is actually extracting how to use this to find an upper bound on this size of x. So let's see how this goes. So you have this set, again, subset of this n-dimensional vector space over F3. No 3 points are collinear. We'll want to prove that the size of x is at most this thing right over here. So I alluded to this already a little bit. The strategy is going to involve 2 pieces. The first piece is find a diagonal tensor on triples of points, knowing that x avoids collinear triples. And then secondly, find an upper bound on the sliced rank, because we know if we find a diagonal tensor, the size of this underlying set is going to be the sliced rank, and then we'll find an upper bound there. Okay, so this is all stuff that was done in the article I mentioned earlier that broke through this exponential upper bound. So let's go ahead and do this. So step 1, here is the diagonal tensor that they created. So let's analyze this a little bit and get a sense of what's going on. So you have a function from threefold product of this set. And the function does something like this. It adds up for any given I, it adds up the ith coordinate of each of the vectors, subtracts 1, does that in subtract 2, multiply all of these, and that's it. And I want to give you a reminder that 3 points in this space are collinear if and only if they're equal in every coordinate or different in every coordinate. Right? Sorry.
N is the size of x?
Sorry, say that again?
N is the size of x?
No, so n is the dimension of this vector space. So each of these vectors have n coordinates.
So that x is a tuple of n.
Yeah, x is a triple, x itself is a set of points inside of here that avoids a collinear triple. Yeah. Okay, okay, so let's get a sense of why this might be diagonal. So let's look first at the situation when all of these vectors are actually the same. So if all these vectors are the same, then they're the same in every coordinate. So for example, this sum right over here would be 3xi. 3 is 0 in our field, so this goes away. You have -1, right? Similarly, here you'd have -2. So you get 2 as a product. Multiply all those, you get 2 to the n. That's never 0 in F3. Okay. Now the question is what happens sort of otherwise, right? So if you're off diagonal, what kind of thing happens? And you can play around and see if, in the off diagonal case that you will get 0 no matter what. Sort of a case analysis thing. Okay, so now because of the fact that this function is actually diagonal, we can go to step 2 and find an upper bound on our set by actually figuring out an upper bound on the slice rank instead. Now, why would one want to do something like this? Well, now you have an explicit function that has degree 2n in, I guess, 3 vector variables, but technically 3n individual variables. So there's ways you can sort of expand this out and try to collect terms and figure things out. Okay. So how do you do this? So the essential idea is just be brave and brute force things, right? So you look at this thing and you literally expand it completely out. Right? So if you look at the form that it takes, you'll have in the expansion of this thing a bunch of xi variables, yi variables, zi variables. Okay, I have to change that to zi variables because I'm moving back to Canada. All right, and the exponents, if you look here, in any xi, the largest exponent you have is 2. So all these exponents here are either 0, 1, or 2, and they're exactly n of them. And so again, the goal is to find a minimal representation of this as a sum of slices, which are functions in the, I want to be careful here, one vector variable multiplied by the other vector variables, right? Because our underlying set here is in terms of vectors. So how do we do this? Well, again, you can sort of brute force things. So you have this function that has degree n. So in these 3 vector variables x, y, z, at least one of the variables in each monomial appears in total degree a third of them, right? So you sort of pull those out and you get something like this. So you take the summands where the x variables have degree at most 2n over 3, take those out, and the rest of the thing that you multiply this by will be in the vector variables y and z. And then you do the same thing with each of the other ones, right? Yeah?
There's something confusing. You say at least one of the variables appears with total degree at most 2n over 3. Do you mean one of the vectors? Because each of the variables?
Yeah, so right. So the question is it confusing what I mean by total degree at most n over 3. So what I mean is the vector variables. Yeah, so it's the, yeah, so when I say monomial, I mean actually like a bold-faced monomial x in the xi's, yeah. Okay, so how do we get a bound on the size, the number of summands that we have here? We can look just at the indices that we're summing over, right? So we have, if we look in terms of the exponent vectors for these slices we've peeled off, the exponents have that the sum of them is at most 2n over 3, and you have 3 copies of this thing. So the total number of slices in this brute force method is at most 3 times the number of these exponent vectors, which is the number of vectors with coordinates 0, 1, and 2 of length n, whose sum is at most 2n over 3. Okay, and we know for various reasons that this thing is going to be less than 3 to the n. If you don't play with these ideas too much, you can think, here's a sort of motivating reason why. Imagine instead you got rid of this 2 and you asked for the sum of the variables to add to at most n over 3, then this number is the sum of the first, like the sum of the binomial coefficients, and choose k up to like n over n choose 3, and so these numbers have like a bell curve shape. That sum is going to be sub-exponential. Okay, so that's the game that is sort of, this was the first introduction of playing this kind of game, but we have a sense now of what this game actually looks like. So there are some questions that come up in this particular example, but then there are a lot of questions that come up in terms of how you progress and use this outside of this particular example. You know, one of the questions is, can you do better than this? But this is so lax, right? I mean, like this is in a sense, this is like the laziest way to get an upper bound, right? You could have focused a little bit more on the computations you were doing to get something possibly better. And there's an article that says up to an exponential factor, actually you kind of can't. Okay, and then there's a question of how you use how this type of process proliferates to other examples. So like I said, the overall strategy we used was, in a general context, would be if you're avoiding a particular property, create your diagonal function, and then upper bound its slice rank when you can do that. And the difficulty that actually comes in, so at this point, like, so I sort of read a few of these articles, and then I read like a ton of these articles and got a sense of how this game is played. And there's a delicate balance that becomes very frustrating, right? So the type of thing that happens when you try to actually employ this is you get a diagonal tensor that gives you a very trivial upper bound when you apply with the slice rank. Or you find something that you just can't make quite diagonal, but you get a good upper bound. And so you're constantly playing this tug of war between these two different competing things that you want to both happen at the same time. Okay, so when this process was discovered, there were a whole bunch of extremal combinatorics type problems that people were able to make quite a bit of headway on, and these were questions that were people didn't have a sense of how to approach well for a long time. And I want to talk about one particular one that gives you a sense of where the efforts that I had came in to start unifying some of the stuff that I saw that these individuals were doing. So that's in this particular article right here about sets avoiding right corners. Okay, so a similar type of problem, in this article they were thinking about maximizing subsets of an n-dimensional vector space over FQ. Q here is a prime power that has no right corner, right? So right corner meaning you have like orthogonality at one particular triple of vectors. So a way that you can be explicit about that is to say you have no distinct triple x, y, z with this particular inner product happening, right? We have a right angle right at z. Okay, so the tensor that they decided to create looked something like this. So you have this object right over here, which is sort of artificially created in a way so that, like, if you think about this field, any non-zero element raised to this is going to be 1, and then 0, you get 0. So if you play around with this particular tensor, you can sort of quickly argue that it actually is not diagonal. It looks more something like this. So it's, if any one of these pairs of variables are equal, you'll get 0. Right? So for example, if y and z are equal, this funny indicator for when y and z are not equal is going to 0 out. Right? And if x and y are the same, you get sort of the same phenomenon here. So this looks a little bit different than what we had before, but they sort of translate this to a diagonal tensor in a sort of natural way. And it looks like this. So you can recognize this as twice the indicator for when all 3 are equal, and then minus the ones where pairs are equal and plus 1. So I'll say 2 things about this. One is, like, you might be looking at this and thinking, okay, I have to sit and like actually compute to figure out that this is the case, right? But a better way for us to get a sense of where this is coming from is you might notice that these coefficients come from Mobius function numbers on partition lattices. In this particular case, partitions of a 3-element set. So that's where I started to notice things. So this is a very like simple example of this type of phenomenon, but I started to notice these numbers come up in a lot of applications, but when people tried to create tensors that were not necessarily diagonal, they did the diagonalization process in a completely funny way that was ad hoc and not related at all amongst themselves. So the advantage of doing something like this is we know that this particular tensor right here actually is diagonal. So if you rearrange, you'll have that the size of, because this thing is diagonal on A cubed, you'll have that the size of A is the slice rank of this thing, which here you have this function that we had up here plus functions that are all slices, right? So you'll get that the size of this set is at most the slice rank of this T plus 3. The thing that I'm omitting here is why bother with this particular expression for this function and doing something that's not diagonal. And the thing that I'm omitting here is all of the mess that you saw when we actually computed the slice rank of the previous function, right? So if they expand this thing and collect monomials of different types and then compare, and it turns out to be that this particular choice of a function is a good one to do that with. Okay, so the key thing I think here is that the way that they created this particular function is that it wasn't diagonal, but it was constant on partitions of the variables, right? So what I mean by that is it's constant if you know, x and y are particularly the same, or y and z are the same, et cetera, et cetera, et cetera. All right, so let me give a different example that illuminates this point even further. So there was this paper in 2020 that tried to employ sort of similar techniques to address the question of avoiding what's called a k-right corner, which is sort of a generalization of what we saw earlier. So you have distinct variables x1 through xk plus 1 in this vector space, and they form a k-right corner if you have that they're distinct and these differences are pairwise orthogonal. So let me show you the tensor that was, the function that was created in this case, and some problems that arise with it, how the diagonalization process worked, and then sort of where I came in to think about this on a more general level in a lot of different applications. So the attempt was something like this. So it's sort of the same game that was played on the previous page. where you sort of like kind of fictitiously create a polynomial where you know that this expression right over here is going to be 0. This expression right over here is going to be 0 only when this particular thing is 0, right? So this is 1 when this inner product is 0, right? And vice versa. Okay, so you have that this particular function is 1 if all of these differences are pairwise orthogonal and is 0 otherwise. But there's something very subtly problematic about this, right? Which is that here we're wanting to think about distinct tuples that have this pairwise orthogonality property. And this does not, unfortunately, account for that distinctness, right? So for example, you could have a situation like this. You could have, say, x1 minus xk plus 1 orthogonal to x2 minus xk plus 1. And then because we're in a finite field, you could actually have x2 minus xk plus 1 orthogonal to itself and set all of the other xi's equal to x2. Right? And then you have a whole bunch of things that are not distinct, but still will make this function 1. So you have to figure out a way to augment this in order to make it a diagonal tensor in order to be able to apply these methods. Okay. So this is sort of a thing that I noticed sort of proliferating throughout all of the literature, is that people were creating, looking at subsets of finite fields that had no distinct k-tuples with a particular property, and it was sort of easy for them to create some type of function that was some constant if all of these variables satisfied the property that they had. But they weren't able to account for the fact that all of these were not necessarily distinct, and that's something that they wanted to handle, right? And it was another non-zero constant if they're all equal and 0 otherwise. Okay, so the idea then is to create some function you can multiply this by in order to actually make this diagonal. Now, the thing I should mention is when I show you like the way to do this, you'll notice that it's kind of a natural thing, and that shouldn't be the substance of like the sort of the article that I worked on this stuff. But I'll give you a sense of what the substance of the actual article was. And part of the reason I evaded presenting it in this talk is because you get this mix of Mobius inversion stuff together with that expansion mess you saw before, and putting those two together in a slide that makes things clear is not a thing that is good to do. Okay, so how do you create this thing? So let me look at actual like examples when I set k to particular values. So let's, sorry, I want to actually mention that, like I mentioned before, this process was done in a lot of these articles in completely different ad hoc ways. Okay, so how do you do this? So in this particular situation, you can kind of do something like this. So you take, let's say k is 3, you can write this, create this function where you have 1 when all of the variables are distinct, -2 when they're all equal, and 0 otherwise. Okay, so let's analyze this just quickly for a second. When you take this and multiply by this, what actually happens? So you're still non-zero on your diagonal. This is the example when k is 3. Right? Now, when you're distinct, you may still stay non-zero, but the subset you're dealing with has no distinct k-tuple, so you don't care about that. Right? They won't show up, and then you're 0 otherwise. So when you actually multiply these two together, you do get something that's diagonal on this restricted set that avoids k-tuples, in this case 3 tuples, of distinct points that have that particular property. And now the thing that's beautiful about something like this is if you're thinking about this from the perspective of trying to apply sliced rank ideas, right? you can use Mobius inversion to just write this as a sum that looks like this, right? A sum of indicators. And now, when you actually multiply F3 and H3, you'll get something like, when you do it term by term, you'll have that the size of A is bounded above by the slice rank of each of these things. And now there's some work to do here, but you can at least do some stuff. So here you have whatever function you're dealing with that's particular to your combinatorial situation multiplied by something that looks kind of identifies two variables. And so you can identify those variables in this function and then do some work to actually compute the slice rank of that particular function. Okay. If you instead were just to like think about the representation of this function as being like, you know, -2 times the indicator where all the variables are equal, you wouldn't be able to compute the slice rank as easily that way. Okay, so what happens when you move from 3 variables to 4? We want a sort of general method. If you move to 4 variables, the similar process would give you, like, using, again, Mobius version on the appropriate partition lattice, you get 6 times the indicator where all variables are equal on A4, but you run into a slight problem with trying to do slice rank type things. And the issue is something like this. If you take this H4 and multiply by F4, you'll get summands that look kind of like this. And an issue with something like this is you have the product of like 2 slices times another function, and it becomes actually problematic to think about what the slice rank of this thing is, because you're identifying some variables and identifying some others, right? So how do you handle a situation like this? Well, you actually invent a different method of thinking about rank. That's what sort of Naslin did. He introduced this concept called Partition-Rank, which refines the idea of slice rank. So in the second step of this process in this game, instead of thinking about slice, you think about this idea of partition rank, which I'll now sort of introduce. Okay, so we'll say a function has partition rank 1 if there's a way now, instead of to slice off one variable, to partition the variables into sets of variables and write your function as a product of functions that are functions of those individual variables in the way you split the variables up. So for example, if I have a function that looks like this is one of the ones that came up on the previous slide. It's 1 if x1 and x2 are equal, and x2 and x3 and x4 are equal, and 0 otherwise. I can write this as a function in the first 2 variables right here, the indicator of that, and a function of the last 2, the indicator in those 2, right? And so very directly, it has partition rank 1. But if you actually try to compute the slice rank of this thing, you get into problems. It's not clear what the slice rank of this particular product is. So in this article, Naslin actually went about doing sort of similar things for slice rank, but in the context of partition, that introduced the idea of partition rank and did similar things that we saw for slice rank for partition rank. So we have partition rank 1 functions, partition rank 1 functions, and he introduced the idea of partition rank in general, which is for a particular function, the minimum number of partition rank 1 functions you can write it as a sum as. So it's a similar analog to slice. Okay, and he had a similar theorem as well that said in the case that your function is diagonal, with non-zero diagonal, the size of your set is actually equal to the partition rank. So in the case where you're actually diagonal, slice rank and partition rank and the size of your set are all the same. But in terms of finding actual upper bounds on the size of your set, it's much easier to deal with this because you're allowed to break up your functions into many more pieces as opposed to what you did with slices. Okay, so coming back here, the objective again was to take something that looks like this and diagonalize it, and we did that by creating this particular sum of indicators that had things that looked more like functions that were on partitions of variables rather than something involving slices. And it turns out, I'm removing a lot of the details, that if you use partition rank instead, the size of A by these similar theorems that Naslin proved I mentioned on the previous page, the size of A will be bounded above by the sum of all of these partition ranks, and these things are much more manageable to deal with because they're represented as products with your individual function and products of functions that use all the variables. Okay, so I have about like a couple of minutes left, and I can give you a sense of the kind of thing that I did here. Like, so from my perspective, like this part was actually somewhat like direct to see, but it was, like I said, it was sort of done ad hoc in a lot of different areas. But the reality of a lot of the applications is they don't even look as simple as this. What really happens instead, I've sort of grayed out what the functions look like. In a lot of applications, the functions are constant on partitions of the variables. So they're not necessarily like just non-zero on the diagonal and zero everywhere else, right? There's funny things happening depending on the way the variables are partitioned. So that's what happens sort of in a very, very general situation. And this article that I wrote talks about how to do the diagonalization process exploiting Mobius inversion when you have this situation happening, which you might think, if you have experience with this stuff, is sort of not a too difficult thing to do, but you also have to sort of respect keeping partition ranks low at the same time. And that's the thing that's hard to do, is doing both of those at the same time. But sort of in this article, I talk about exactly how to go about doing that in many, many different contexts, right? And so some examples of things I was sort of able to talk about is how to take these ideas that Naslin had dealing with just these particular types of tensors into ones that look a lot more complicated than this, where you have lots of different values depending on the way the variables are partitioned, and then sort of answered a bunch of questions, finite field analogs of questions that arose sort of throughout extremal combinatorics, but all under this same umbrella and framework, right? So a lot of these sort of came out of thinking about this idea and employing the things that I built up here. Okay, so that's like almost exactly on time. I'm done. Thank you. Oh, thanks.
Questions? Yeah?
Great talk. So in your definition of partition rank, I missed it. Do you want to assume that your partition has at least 2 blocks? And also, can you say something if your partition has a lot?
Oh, yeah, okay. So, yes, at least 2 blocks. Sorry.
Oh, I'm sorry.
Oh, right. So, right.
Yeah.
Okay. So the question was in the definition of partition rank. So let me start with partition rank 1. So in the definition of a partition rank 1, do you want at least 2 blocks? Yes, you do. And so the next question was, what happens when you have many blocks versus few blocks? So this is actually, when it comes to infusing this stuff into the, especially when you're dealing with infusing the Mobius stuff into the partition rank theory, The thing that happens is you get better bounds sort of the more blocks you have. Yeah, so the game is to try to sort of minimize that. So one of the things that I noticed that I talk about in the article is it wasn't framed this way in the application that one of the papers used, but they essentially said something like, you can ignore the situation where you have 2 blocks and just use 3 or more and get better bounds. And so I sort of interpreted that in terms of this theory that I built. Yeah. Yeah, Justin.
So the partition rank being less than or equal to the slice rank means that there could be situations where you can get an upper bound using slice rank, but you can get a better upper bound using partition rank. Is that something that has come up or that you've seen?
Yeah, so there's this whole thing, there's another notion of rank. Sorry, question, yeah. So the question is, partition rank has slice rank as an upper bound. So the question is sort of like, let me make sure I got it right. So your idea is like, are the situations where partition rank does like a lot better than slice? Yeah, there are. That's like a big thing that's talked about sort of in this paper and done in a lot of the other papers. Yeah.
This notion of diagonal seems pretty rigid. Is that the only class of tensors for which the slice or partition rank can be bounded effectively? Like, why all those diagonals?
Okay, so the question is, the condition of being diagonal seems quite rigid. Are these only classes where you can get good bounds? So there are others. One of the things that gets sort of complicated is when you're trying to infuse in particular combinatorial situations. So like you can get, when tensors are not necessarily diagonal, you can get some good bounds. The problem is when you try to apply in these settings, then things get kind of haywire. Yeah.
There's a question up there.
Yeah.
Follow up to the first question. So if I understand correctly, that all rank functions might be evaluated to use only 2 blocks because you can use the other multiple blocks into one. So
Say that again, sorry?
So for the definition of partition rank, I think if you just disallow 1 block, then I think all rank functions is written as the part of 2 blocks. Because if you have 1 or 2 blocks, then you just fuse them into 1. If I understand correctly.
I see what you mean. Yes.
Again,
so the question is, why not think about all partition rank 1 functions as being represented by 2 blocks instead of refining more, right? Yeah. So the advantage of doing a more refined thing is that when you actually go to do the computation in a lot of the settings, you get a lot of better bounds when you do refinement instead. Yeah.
I have a naive question myself. I don't suppose there's any chance the Mobius function of the k-equal partition lattice could do anything.
I thought about this, so yeah, that's a good. You asked it on the mic, so I don't have to repeat it.
Right.
Yeah, I thought about this, and yeah, I think actually there might be something there. Yeah.
Okay. We have time for one more quick question or an extra long 5 minutes. Oh, go ahead, Joel.
Just an enumerative question. Do you know anything of the distribution of partition rank over all tensors of fixed chain, like fixed Q, fixed?
No, I think even the question of just like pick small numbers and count is not known. Yeah.
And can you repeat the question?
Oh, yeah, I'm always doing this. So the question is, do you know something about the distribution of partition ranks for, I guess, given tensors over a particular set? And it's really not known. I spoke to like Nathan Kaplan a little bit about this because he thinks about these things. And we tried to compute in very simple situations, and yeah.
Any further questions, you should ask him later. Let's thank the speaker again.